Okay, good evening, children. Here we are with physical property of amines. The first physical property that we are doing is physical state. It is seen that under normal condition, amines with one carbon atom and two carbon atom are gaseous. They are gaseous with fishy smell. Say this amine, it is a gas. Ethyl amine, it is also gas. They are gaseous, and more than 3 carbon atom, they are liquids. They are liquids, and amines with many carbon atom, they are solid. Let me tell you is this aniline with 6 carbon atom is liquid. It is liquid. Now next physical property is we discuss about solubility. As in other type of organic compounds, lower amines are soluble in water. For example, this amine will be soluble in water because they can form hydrogen bond with water. CH3 and H2. So this methylamine, and it can form hydrogen bond with water because this is delta minus, this is delta plus, and water, which is here delta minus and this delta plus. So there can be hydrogen bond. So that's why lower amines are soluble in water, but higher amines where the non-polar character will dominate, there hydrogen bonding cannot be formed, hydrogen bond formation doesn't take place. So that's why higher amines are insoluble in water. So those amines will be definitely soluble in organic solvent. Okay, now one question, suppose butane 1 amine, CH3, CH2, 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 NH2, butanamine, and say butane 1 all, CH3, CH2, 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 OH. Which one will be more soluble in water and why? Now since NH bond and here OH bond, since O is more electronegative than nitrogen, in Pauling scale electronegativity of oxygen is 3.5, of nitrogen it is 3. So electronegativity difference here will be more and here will be less. So this, since it is more polar, that's why solubility of this one in water will be more than this one. So butane 1 all is more soluble than butane 1 amine. Okay, coming to next physical property, that is boiling point. Boiling point. Now it is said that among isomeric amines means amines with molecular mass same or with molecular composition same. This is the order found. 1 degree amine has higher boiling point than 2 degree amine. 2 degree has more than 3 degree amine. This is found. For an example, say butanamine butyramine has a higher boiling point than, say, let us make a secondary amine. Secondary amine means with NH unit. Secondary amine will have a NH unit, so we can keep 3 carbon atom this side, 1 carbon atom this side. So this is secondary amine. Boiling point of this one is more than this one, and this in turn will be more than a tertiary amine. Tertiary amine will have no hydrogen attached to it, all alkyl group. So total of 4 alkyl group we can keep on one, 2 carbon atom, another 1 carbon atom. So this is the boiling point order. The reason is that here, since there are 2 hydrogen per molecule with N, there will be hydrogen bonding, but here also there will be intermolecular hydrogen bonding. But since here it is NH2, here it is NH, more hydrogen here, here there will be more extensive intermolecular hydrogen bonding. Intermolecular hydrogen bonding will be less here, less extensive here, and but in this case, since with N there is no hydrogen, so tertiary amine doesn't have intermolecular hydrogen bonding, and that's why its boiling point will be the least one. So this is about the boiling point, and this is quite obvious, as number of carbon atom will be more, boiling point will also be more. Okay, now next property that is you can say physical also, chemical also. It is that amines will be basic in nature, because you see all these amines, there is a nitrogen lone pair. There is a nitrogen lone pair which can be donated, that makes amines basic in nature. So let us discuss this point. Okay, so here we have with basicity of amines. Suppose a amine is dissolved in water, so there will be an equilibrium. There will be equilibrium because this one will be able to accept a proton from here, and it will become RNS3 plus, and this one, after losing a proton, it will become OH minus. So there will be a hydroxyl ion in the solution. So we can say that amines are also RNase base. Amines having nitrogen lone pair can donate lone pair. So amines are Lewis base. At the same time, in aqueous solution, since it is giving hydroxyl ion, so we can say that amines are also RNase base. So now this equilibrium will have a equilibrium constant, product by reactant, and this on rearranging we get K into concentration of water, this one, and since concentration of water is constant here, so this constant multiplied by this constant, we get a new constant, we call it Kb. B stands for base, and so this is the expression for Kb, and you have done this thing in class 11, that higher the value of Kb, more basic will be this compound, more basic will be amine. Okay, and there is another term that we use for considering or comparing basicity, that is pKb. We use pKb, whose definition is minus log of Kb. But here this thing happens, that I am writing it here, more basic more basic, greater Kb value. And in terms of pKb, your more basic, lower pKb value. So this thing you have to know. Okay, you in exam you may be given the pKb value, so you have to understand accordingly which one is more basic, which one is less basic. Okay, now a simple question here is, say say RNH2 and ammonia. Between these two, which one is more basic? Now RNH2 will be more basic because alkyl group has a plus I effect. Alkyl group has a plus I effect, and due to this plus I effect, lone pair availability over nitrogen is going to increase. That's why this one, or amines are more basic than ammonia. So you should always remember, amines are more basic than ammonia. Now between RNH2 and ARNH2, between RNH2 and ARNH2 means aromatic amine, and this is aliphatic amine. Aliphatic amine will be more basic than aromatic amine. Aliphatic amine will be more basic than aromatic amine. So how can this be explained? You have to let us take one example of aromatic amine. One example of aromatic amine is aniline. So aromatic amine is aniline, and here what will happen is there will be resonance. And what resonance? Plus R will be taking place, and due to that, this lone pair will come here. This pi bond will break. It will come over here. So one resonating structure will be and likewise in the next structure, this lone pair will come over this place. In the next structure, lone pair will come over this place. So like this way resonance will take place, and we can understand from here is that lone pair availability, because of resonance, because of plus I effect, is going to decrease. Is going to decrease here because of plus I effect. The lone pair density is increasing, and that is the reason why aliphatic primary amine is more basic than aromatic primary amine. Very important. Okay, now if you are asked to compare the basicity of aromatic primary amine and ammonia, aromatic primary amine and ammonia, now here ammonia is more basic. Ammonia is more basic. It is because in case of aromatic primary amine, as you can see here, there is a decrease in lone pair density taking place because of plus I effect, or because of, we can also say, because of minus I effect of benzene ring, minus I effect of benzene ring. So aromatic primary amine is less basic than ammonia. Now, what will happen if the order of amines are not same as far as basicity is concerned? The order of amines is not same, then we have like these situations. It is seen that in gaseous phase, uh, 3-degree amine is more basic than 2-degree amine, which is in turn more basic than 1-degree amine, which in turn is more basic than ammonia. Say as an illustrative example, say we have here CS3, N, CS3, CS3. So this is an example of 3-degree amine. This one will be more basic than CS3N, CS3. This one will be more basic than CS3, NH2, and this is more basic than ammonia. In gaseous phase, this can be easily explained by the Plaza effect. Here there are 3 Plaza effects. So whereas here there are only 2 Plaza effects. So lone pair density will be more here, and here there is only 1 Plaza effect. Here there is no Plaza effect. So this is the order of basicity among amines of different order in gaseous phase. But the order is not like this in aqueous phase. In aqueous phase, if we are considering a solution, in aqueous phase, the order is found to be like this. 2-degree amine now is most basic, then 1-degree amine. 1 degree is more basic than 3-degree amine, and 3-degree is more basic than ammonia. This is the order in aqueous phase. And one more thing that has to be mentioned here, this order is applicable for smaller alkyl groups. For smaller alkyl group, this is applicable. That is for methyl system. That is suppose in aqueous solution, CS3N, CS3NH. This is most basic. Then it will be CS3NH2. Then it will be CS3N, CS3, and least basic will be ammonia. So why is the order like this? That we need to understand. Now here, in addition to Plaza effect, there will be another factor involved here. In addition to Plaza effect, here the factor that will be involved will be solvation factor. Solvation factor or solvation effect. So what is that? What is that effect? Now, if this is the base, now the conjugate acid of this will be CS3NH, CS3H plus. So this is the base, this is the conjugate acid. Similarly, the conjugate acid of this base will be CS3NH3 plus. And in this way, the conjugate acid of this you understand, and this one you can understand. Now, what is solvation effect? What is solvation effect is what is solvation effect is suppose this base, its conjugate acid is N H H H H plus. So this is the conjugate acid of ammonia, and solvation means in solution this cation will be surrounded by solvent, will be surrounded by water. In this way, water, which is H2O, you can also write it as OH2. So it gets hydrogen bonded. When it gets hydrogen bonded, energy is released and this becomes more stable. So it gets hydrogen bonded with water. This one also gets hydrogen bonded with water. This one also gets hydrogen bonded with water. So in this way it gets hydrogen bonded, in this way it gets solvated, and when solvation is taking place, energy is released. When energy is released, the conjugate acid becomes more stable. If conjugate acid becomes more stable, then basicity becomes more. Basicity becomes more. So to compare the basicity of these amines in aqueous solution, we have to consider Plaza effect as well as the solvation factor. Now, considering both of them, this is found to be the order. Okay, because here in case of 2 degree amine, Plaza effect also is there, and there is also a considerable amount of solvation effect. Why ammonia is least basic? Because here it has good amount of solvation factor which will stabilize the conjugate acid of this base, but as you can see there is no Plaza effect. So in this way, taking into consideration both the solvation factor and Plaza effect, we can explain the order like this. But what happens with bigger alkyl group? If alkyl group is ethyl, if the alkyl group is propyl or bigger, then the order is found to be like this. Then the order is like this. And the order is like this. Like for bigger alkyl groups, the order is found to be slight change, like 2 degree is still most basic, and now there will be a change, in the order. 3 degree will be more basic here, and then it will be 1 degree, and then it is ammonia. This is the order in aqueous phase for bigger alkyl group. So here we can briefly explain why 3 degree is more basic than 1 degree. It is because now in this case 3 factors will be involved. Not only Plaza effect, not only solvation effect. Here there will be another factor that will be playing, that is steric factor. Steric factor will also be there. Now, what is steric factor? Suppose let us consider this 1 degree amine, say with 3 carbon atom. So CH3, CH2, CH3. Okay, let us consider ethyl in less space. So this is 1 degree amine, and the conjugate acid is, this is the conjugate acid. Now, solvation takes place. Normally solvation takes place, so OH2 dot OH2 dot OH2 solvation will take place. But what happens is that because of this group very big, there will be some hindrance to this solvation. This bigger alkyl group will create some hindrance to this solvation. So solvation will not take place as much as it was happening here. Solvation effect will not happen because of bigger alkyl group. So that is the reason why 1 degree amine becomes less basic than 3 degree amine. 3 degree amine is more basic because of more plus I effect. So for bigger alkyl group, this is the order of basicity of amines. So children, we will do this much only for now. Here in exam you will find many questions on arranging amines according to their basicity. Many amines will be given to you, okay, and you will be asked to arrange them. So this order, all this order you should remember. Maybe you may not be asked the reason, but you have to remember the order. For example, in gaseous phase, it is 3 degree greater than 2 degree greater than 1 degree greater than ammonia. In aqueous phase for methyl system, it is 2 degree greater than 1 degree greater than 3 degree greater than ammonia. And in case of still bigger alkyl groups in aqueous solution, it is your 2 degree greater than 3 degree greater than 1 degree greater than ammonia. So if you remember this, then you can easily do such type of questions. So this much for now. Good night.